Well, we wait another few minutes because not all students are in yet.
Yeah. Problem solving. That's ja, dan boven de studie die er vaak dat is zonder iedereen humaan af. Dat is dan Koolman en de nee. Dat is ook dat zijn wedstrijden. Dit is niet een wedstrijd, het is gewoon voor plezier. Ja, dat is ook een wedstrijd. Nee, dat denk ik niet. Ik denk dat al die PSA's gewoon dan als het is op de computer en dan is gewoon niet zo ik daar uitgeven en dan los we een paar oefeningen, maar dat is gewoon heel veel, ja. Maar cool, maar dat is wel een wedstrijd. Is ook nog een cool, maar of zo, dat is ook een wedstrijd, maar dat is misschien wel zo. Die er ook aan komt.
Zo ben ik daar.
Ik hoop niet dat het ook maar dat is echt mijn concept. Maar het is van die mensen gaan met de Koreaanse familie. En ja.
Wat is de beste?
In de coma.
Ik ben de beste, maar ik ga waarschijnlijk niet meer doen.
En anders gaat het maken.
Ja. Allee, Toon en Steven gaan waarschijnlijk ook meedoen. Die gaan ons allemaal afmaken, dat denk ik ook. Maar het is dus de beste categorie, dus alles is oké.
Ja, ik was een essay aan het proberen van Rubican. En dan zei het tegen Rui, ja, dat is keigoed essay. Dan zei Rui, oké, wij zitten in een team, maar ik ga spijt aan lot. Ik kan niet zo goed voor.
Wat is met andere studenten?
Willem nog?
Goeie vraag. Misschien naar leslokaal 3.2.
Ja. Misschien kun je even een tekstmail sturen als in.
Ja, we willen dus ook wel eens te laten komen.
Ja. Okay, I will slowly start. So, and everything will be quite elementary today. So, I will speak phase transitions. In Wednesday. Now, what we will cover in this part is elementary Ramsey theory for pairs. So it's not Peres-Harrington theorem in full generality, but just in dimension 2. So Peres-Harrington with dimension 2 is the following statement. For every E is true, where C and M, there exists a Ramsey number R so big such that for all partitions P, from the two element subsets of the predecessors of R into C many colors, there exists H, homogeneous set, such that P, when restricted to the two element subsets of H, we get constant value. And on top, the cardinality of H, at least as big as a number M. At least as big as a maximum of M and the minimum of H. Now, what we will learn in this lecture is that R, depending on C and M, will be non-primitive recursive. Moreover, we study Berry-Seddington with respect to parameter function f. And we will figure out for which functions f the statement is complex, producing the Ackermann function, and for which functions f we get simple bounds, simple upper bounds for the Ramsey numbers. Now, first of all, question is EH true? Even this is not clear from the beginning. So first we'll learn why this is a true statement. For this we have to do small experiments. So the answer is yes. But now we will give an explanation. So first of all, we show Ramsey theorem. And we will use the infinite version. Now look, this Berry-Seddington assertion is just speaking about finite objects, but the infinite Berry-Seddington statement, infinite Ramsey theorem is something different. So the following theorem. So let E be a partition function like here, but now working on the two element subsets of an infinite set. We take here the natural numbers. And we go into a finite set of colors. And then there is infinite H. Such that E, when restricted to the element subset of H, we obtain constant value. And already this is difficult to prove. So when you have never seen the proof, well, can give it a try, but it's rather complicated. Now in discrete mathematics, you may have seen the pigeonhole principle, which is easy. When you split an infinite set into finitely many parts, one part has to be infinite. And this idea has to be iterated. And this is what we are going to do. So proof. So let E be a partition. Well, now we consider sub-problems. We fix an element in the natural numbers. The first element which we fix is the natural number 0. Consider what? Natural numbers without number 0. And let C be a function from this set. into a set of C many colors, just defined by using a function P. So C0 of y is P of 0 and 1. Now this is a function of an infinite set into a finite range. So one of the three images will be infinite. Fine. There's an infinite C U0 such that C0 when restricted to U0 constant value. This looks good. So what does this mean? We have elements in U0. Well, then P of 0, one element in U0 is the same as P0, another element in U0. So it looks like we have an approximation for the homogeneous set. But of course, for the final homogeneous set, we also have to consider inputs for P where the first element is not 0. So this is, of course, not the one which we finally look for. Anyway, we have the first set. Now we enumerate the elements of U0 in increasing order. And first, we put this element 0 aside. Call it 0. U0, 0 is 0. And enumerate U0 as 0, 1, U2. That's it. And we know this is infinite. Okay. Next thing what we do is we now consider a new domain. We work on this domain and pick out the first element. So U11, first element. And now we iterate this construction. Consider function C1. C1 now works on U0, where the first element is limited. And we induce C1 by using function P. P1 of y is P1 of P U11. What does this mean? If again a function working on an infinite domain into finitely many colors, so one preimage will be infinite. So there is a U1 infinite such that C1 of U1 when restricted to U1 is constant. And U1 is infinite. Now, what we do is we enumerate the set. Let U1, U1, 2, U1, 3, U1, 4. That's it. Let U2 be the first element in the set. Now iterate the construction. So we find capital U2, U3, etc. Looks good. Finally, we go into the diagonal. Let B0 U00 B1 B11. Then we'll let VI equal to UI. Now it's not the case that this diagonal set is already the final one, but by construction, we find what? P VI plus 1 is the same as P VI J, or J bigger than 1. Now that is just by construction. Because we have used the property of capital U index time. Now comes the final application of Fignon principle. Let C the coloring from natural numbers to Z. P I is what? P I plus 1. Now C goes from an infinite set into a finite set. So one of the pre-images is infinite. If U is infinite, such that C when it is to U, it's constant value. And now we finish the proof. We can define the homogeneous set. So let H be the set of EI, I is in U. And that is our final homogeneous set. Why is this the case? H is homogeneous for okay. Well, why is it the case? We start with 2 elements, I, J. And we consider P. What is this? You have this property star here. That's the same as E, VI plus 1, which is the same as CI. Now we take some other elements. Let's say VL and VM. That is one of the names. We take P over E. By the same argument, using this property, this is the same as E, L, plus 1, which is the same as CL. Now the indices are new, C is constant on it, they're the same. So that's a magical proof, very nice one. And if you haven't seen it before, it's difficult to find it because you construct, you generalize, and now the same proof works when you modify 2 into an arbitrary number d finite, but then the argument becomes even more complex. But don't worry, I will not treat it right now. There will be another important theorem. Yes. So then we have the first theorem over here. Then the theorem infinite burden. Now comes what is called Königs lemma. Königs lemma is the main tool to create finitary statements out of infinitary statements. Now, it shows up in different contexts. It shows up in analysis when you prove the Heine-Borel compactness of the unit interval. It has to do with topology, but don't worry. We treat it in the most elementary way you can imagine. So, for this, we have to introduce some notation. And what is the notation? Well, a tree, a new version of tree. In this context, for Königs lemma, it's definitely not tree. Tree is a set of finite sequences. So, of the form x1 to xn, n is at least as big as 0. And we assume that the entries are natural numbers. Now, this is not yet the right definition. This is a set of finite sequences such that this set is closed under initial segments. But if a sequence x1 to xn is in the somewhere between B, if the sequence is in B, and if we have m smaller than n, then the initial segment from the sequence up to m is also in B. If m is smaller than n, then it's contigs m is in B. Now we need a picture. So how does the tree look like? We have the root. The root is coming with an empty sequence. And now we can look at the next level. And the number 0 forms a sequence of a node which is completely to the left. Then there's 1, we go over here. And what's going to happen is such trees could have infinite branching. So for every number n here, could have something like this. And then we continue. For example, when we want to go 2 times to the left, we take the limit over here. And we could go over here. So how to think about this? The finite sequences are addresses of positions in the tree. But this is not in general not a finite tree. It can branch as much as it can be. It's not demanded that we, so it could be that this node is not in the tree. It's just some set such that when you are in the tree and you go downwards, all nodes below are all in the tree. This is what we expect, right? And that's the only requirement. But the tree is somehow ordered by the numbers in the indices, so you know what is left in the tree, what is right in the tree. Okay. Now, what is path in a tree? An infinite path. is what? Well, it's basically something like this. Going to infinity. Now we have to formula this. Fast is given by an infinite path, and V is given by function F when such that for all n. The following sequence is in V. So we have F0, F1, Fn. So for all natural numbers n, I have a sequence of length n plus 1. And so there is no bound, it goes more and more upwards. But actually, I'm not speaking really of a tree where you have really a node which has looked onwards infinitely many predecessors, but it is an arbitrary height in the tree, and this is sum of path. Okay, and what does it mean that the tree is finitely branching? It means that is not the case, and at some node we have infinitely many direct successors. So B is finitely branching. If for all nodes the set of direct successors M such that this is in B. Is finite. Well, what does this mean? We go to some position in the tree, and if you look upwards, there are only finitely many direct successors. And there's an obvious way of defining what it means that a tree is finitely branching. Okay. What can we do with this node? For the famous theorem by Koenig says following. Finitely branching infinite tree has an infinite path. Now this looks completely trivial. It is, in some sense, also completely trivial. So the proof is also obvious, but the trick is actually it's a strong proof principle, and we'll see it in a minute. So the proof. First of all, you would say, yeah, well, I would leave this. I would believe even without a proof, right? But now we do the proof, and then you are more convinced that it's true afterwards. So here. And instead of writing down formula mathematics, I will do a picture. So here is our infinite tree. And here's the root. Now the tree is finitely branching. What does this mean? This means the number of direct successors of the root is finite. Okay, and then we look at the subtrees that are emerging from the direct successors. Now, one of these direct subtrees has to be infinite. Otherwise, by pigeonhole, the whole tree would be finite. Okay, we now choose one of those. Assume this one is infinite. Well, what we do is we take this one and then we jump onto this one. Then we check, well, this is a finitely branching tree, and the whole tree is finitely branching, and therefore at this node, there are finitely many direct successors. And then we repeat. If here's the subtrees joining. One of those subtrees has to be infinite. We choose that one, for example, this one. And now you see, in a recursive way, you can find your path, right? You just every height, you find a point where to go. This finally gives the function f. So that's not a difficult proof, right? But when you have never seen it, it requires some sort of work. Okay. By the way, this is now used in Ramsey. We want to see an application of this. The next application is a finite Ramsey theorem. So there are two ways to prove the finite Ramsey theorem. One is to do a construction by hand. The other one is to apply Königs lemma to the infinitary version. And we will do the second one. There's a certain reason for doing so. Namely, the proof proves the finite Ramsey theorem, but also the Peres-Haring theorem for dimension 2. So what we show next is theorem 3. Finite Ramsey. And what we for finite Ramsey theorem for dimension 2. So for all E and M, this is angle number R, such that for all participants P from the subset of R into C many colors, there exists only this set H, such that P, when restricted, is the subset of H, its constant value, and the penalty of the real set is equals M. And as I said, there are two ways. The direct proof is basically you take the proof of the infinitary version, and then you do finite combinatorics calculations during the proof, but this is a messy proof. The advantages and disadvantages. The combinatorial proof also gives the bound for the Ramsey number, so that's an advantage. Disadvantage is it's conceptually not so easy. Now we prove this one using theorem 1 and theorem 2. And how can we do so? Well, the proof is indirect. Proof. Assume theorem 3 is false. Then there exist certain numbers C and M with strange properties. There are fixed numbers C and M such that, well, now we have to negate the statement. So for all numbers R, what's that for all R? What is a bad partition? Partition P from the two subsets of R such that every homogeneous set for this partition is small. Such that every E homogeneous set H, we have LQ of H more than M. Okay, and now we collect these bad partitions into a tree. Let B be a following set. Sets of partitions P defined on the domain R. P has no homogeneous set of identity. And this is M. Now, two things. Of course, this is not a tree in the usual sense, but when you take a partition and you make the domain shorter, you replace R by R minus 1. Then, of course, if a partition is bad for a big domain, it's all bad for a small domain. So this set B is closed under initial segments. However, B is also finitely branching because you have only finitely many colors to distribute. So if you have an element B defined on domain R, and when you extend it to a domain R plus 1, you have finitely many possibilities to extend the tree, but not more. B is closed initial segments, and B is finitely branching. Okay. Now, for every R, find an element P in B. This means we have an infinite tree. B is infinite. So in this situation, we'll do some minor adjustments. We can apply Koenig's lemma. So what's going to happen? Let E be a path in P. We'll assume P is basically a collection of sequences become bigger and bigger, longer and longer. Then we can basically induce now a partition by taking, well, these are all end extensions of each other. So if you have two elements in a path, one is longer than the other. So the bigger one, when restricted to the domain of the shorter one, gives the shorter one. Then the union over P, it's a well-defined function. It goes from pairs of natural numbers into C. So when we take a path in this tree, it defines, by gluing together the pieces, an infinite partition. Now we have an infinite partition, an infinite domain, I don't have many colors. Now we can apply the infinite Ramsey theorem. Infinite Ramsey implies that there's an infinite homogeneous set. So that exists H infinite, such that union over P, when restricted to two subsets of the H, it's constant value. Yeah.
So it's a when the sentence lets P be a path in
Indeed.
B, does this mean that you mean P to be an infinite path or just finite?
Infinite.
Infinite. You're applying the Queen's.
Yes.
Okay.
So that's important. So there are two things. We look for complicated finitary statements, and the usual way to prove them is you need some sort of infinitary statement in the background, and it's always that we then apply Queen's lemma to generate a finitary statement out of it. And so what we do here is we assume that the finitary statement is wrong. Then we make a finitely branching infinite tree out of the statement. Then we choose a path. It gives an infinite situation where we can apply the infinitary statement. And we find an infinite set homogeneous for the partition induced by gluing together. Now this is infinite. The trick now is then H contains at least as many elements as M, as number M. Here we have the number M. Now, an entity of H is at least as big as M or M plus 1. Doesn't matter. Now, what do we have? Here's our infinite set H. And we take the first M elements here. Right? And then we cut off here. So if you have cut off here, you have here a number R big enough such that one of those R's is bigger than the maximum of H. And then we choose the corresponding partition defined on this R. And then suddenly, with this partition, we would have a homogeneous set of cardinality at least as big as M. But here we have said it's not possible. Such a partition is not allowed to have a homogeneous set of cardinality M. That's finishing the proof. So you see, it's magic, and you don't really see what's going on. You don't see what bounds you have, but you see a nice principle. The nice principle is proving combinatorially complicated statements works always like this. You need an infinitary statement in the background. Then you assume your finitary statement is wrong. Then you apply Koenig's lemma, and then you derive contradiction. And of course, the finitary statements are modeled so that this proof goes through. You cannot, of course, this doesn't work for any combinatorial statement, but the ones which emerge by nature from infinitary statements. Now, why is this proof interesting? Because we make a new theorem and the same proof. And the other version is the definition of H. That means that it gets the maximum of M and the minimum of H. Now you see why the theorem is so interesting. For free, you get the second version, the paraceric dimension 2, also for free. And this doesn't work for the finitary proof of Ramsey, because the finitary proof of Ramsey can be done with imperial arithmetic, but this one can still also be done with imperial arithmetic, but it's very difficult to prove this. Well, how does the proof go? Just the same proof, copy and paste. To assume that theorem 4 is false. Then there are again fixed numbers C and M, such that for all R, there's property that all that's for all R there exists a bad partition. Now what does this mean? For all R there is a partition, bad partition, such that for every P homogeneous set we have that the canality of H is smaller than the maximum taken over M and the minimum of H. So just the usual way of deduction proof. Here it's the same. We have maximum of M and minimum of H. For the same reason as before, this is what? It's closed under initial segments. Well, if the partition on a large domain has no large homogeneous set, then if you restrict the partition to a smaller domain, the smaller function cannot produce a more complex homogeneous set. So it's closed on initial segments, and B is finitely branching, has to do with the property that if you extend by 1, we have only finitely many options to extend a given partition to a longer partition. Of course, we have finitely many cards. So, by magic, Koenig's lemma, we find an infinite path. Fine. And then, by routine, we glue all the elements of the path together to one big master partition. It's over here. Then we apply infinite Ramsey. We find an infinite set such that this infinite set is homogeneous. And now we have to modify the argument slightly. Namely, what are we doing? The trick is as follows. You have an infinite set. So that's our set H. H has a certain minimum. Let's say A0 is minimum H. Okay. Now, here's let's say the minimum is 0. And now we consider A0 elements in H. So we choose a large chunk, is H, such that here at least as many elements as A0. and m. You can just do so because this h is infinite. So it takes a minimum, it's a fixed natural number. We can take finite part of the infinite set, but as big as the minimum. And of course, we also can make this element, the set h restriction, big enough also to have more than m many elements. And then we have the same contradiction as before, right? Then we look at the number r, so big that this homogeneous set is bounded by R. And then we take one of the partitions having domain so big that all the elements in H are contained, and then I do the same language. So that's magic. And this proof is very elegant and extremely powerful. Now, actually, we have next theorem, and it's about for every function f, you can do this. And what we do is here, we just take a0 is basically f of the thing of h. Whatever function f is, if f is exponential function, what's going to happen is, because the I0 is a finite number, we have to go a bit further to the right. But whatever function we take, double exponential function, the same proof works. So you see how powerful this argument is. One proof gives it all. Aha, that is the first result which I wanted to show. Now, the next one is the classification of the Ramsey numbers of Paris Hamilton of dimension 2. And for this, I have to work with the Ackermann function. And now the question is, have you ever seen the Ackermann function before? If not, I could give some more explanations. Otherwise, I just go into the business. So maybe what I could do is I will record some basic facts about the Ackermann function, some easy stuff. For this, I consider the primitive recursive functions. Now, the primitive recursive functions are a subclass of the computable functions. They are the least of functions, but yes, we have first of all some starting functions. We have the function constant 0, 0n is primitive recursive. Then we have the projection function, an n-array function projecting to the coordinate, and the successor function. Second, if we have functions g, let's say, from n tuples of natural numbers, and if you have functions h1 to hn, n tuples of natural numbers, then the function, position function, g, composed with the vector function or the primitive function. Now, how does this function work? This function gets inputs from an n-tuple of natural numbers. We calculate function values h1 of input, hm of input. This gives an m-tuple of natural numbers, and this is now given as an input for the function g. then we calculate the result, and that's composition function. So what should we expect? And 3, if T goes from n to n, H goes from n plus 2 to this, then you can define a new function, an f, and numbers, primitive recursive, is this, and this. These are primitive. And if these two are primitive, then the following function f is primitive recursive. Where now what? F of 0, g of x, f of x is h of x and y. The previous function f of x defined as argument y. So if you have recursion along the last argument, and if g and h are primitive recursive, then f is primitive recursive. Now, using these schemes, you can show easily that all the functions which you see in real life, all functions from natural numbers are primitive recursive. So the usual laws for addition, multiplication, and exponentiation follow the scheme here. We fill in the right definitions, and they're all primitive recursive. Now, what you're interested in is you're interested in a function which is not primitive recursive. That's a function which emerges from this Perestrelnik statement. And what I give is a small extra argument y. These, well, the Ackermann function is so strong. Now, first of all, I have to say what is the Ackermann function, and there are different definitions. And I choose one which is fine for the purpose. So the Ackermann function works as follows: A0 of m is a successor function. This is not a spectacular function. Now I assume that I have defined a of b, and I define a of b plus 1. What I do is I take this function and I iterate it m plus 1 many times, and then I apply it to argument m. And in the limit, I take a of m, it's the general function for one of them. Now, why is this function a growing so quickly? A1 is a successor function. A0 is a successor function. A1 is iterating the successor function, so A1 of n is basically 2 times n. But now, if you have 2 times n and you iterate 2 times n, you get 2 times 2 times, you get the exponential function, 2 to the n. And then you iterate the exponential function, you get the tower function. Then you iterate the tower function, you get big stuff. And of course, if the index here is 10, you get functions for which you cannot calculate the digits on a computer. Anyway, this function has 2 properties, lemma, what you would expect. Namely, every function AD is monotone, strictly monotone. It's proved by induction on D. It's obvious, so to say, because all what you do here is decompose the strictly monotone operations. And of course, a D of n is equal to AD plus 1 of n. And it's also pretty obvious from this definition. That's the reason why I feel the plus 1. This follows basically from the definition of it. And if you just kill off many applications over here, then you have AD plus 1 is at least as big as AD of M. And now comes the theorem. Classical result by Ackermann, 100 years old. For every function f, primitively recursive, let's say f goes from n to n, back. There exists number d, such that for all inputs x, we have f of x is bounded by AD of x. Now we take here the maximum f over x. And for technical reasons, take a number 2. And in the usual course on computability theory, we spent here normally 1 double hour to prove this, but you use a slightly different version. Now we spent 5 or 10 minutes on this. The trick is here we have a faster version of the Ackermann function, so that the proof is almost trivial. But it's not completely trivial, but it's not so difficult. So we have to go through this definition and just check. Right? So proof. By induction. On the generation of the history of function f. So how could f possibly be generated? Well, we look, there's this definition, and we have here some starting functions. The constant zero function. And the constant zero function is bounded by a0. It's fine. The projection function is also bounded by a0. Because the projection function goes to argument xi, but here we have a0 of maximum all arguments, also fine. And the successor function is bounded also by a0. So if you have f generated by 1, you're done. Now, the next step, we assume that f is composed by previous functions g, h1 to hm. So assume f is g composed with h1 to hm. Well, our induction hypothesis says what? These are functions coming earlier in the history. You find these indices for these component functions. So there exists numbers, let's say e, e1 to en, such that e of x is bounded by a e of maximum of x like this. Now one has to be a bit careful in this vector notation. I use vectors of the length appropriate for the input. I don't bother too much. And for every function hi, I have this one is bounded by a with I of maximum. And now the obvious idea is maybe I'll take here an E0. Oh no, E is fine. Now what we do is we go to the maximum of all of these indices. For number D, the maximum over E1. What's going to happen then what? G, so f of x is g of h1 of x h and s. Okay, what do we know about g? G is bounded by this function. So this is bounded by a e maximum over the h I of x and 2. And the HIs are bounded here. So this is bounded by E of, and D is also, and this is big as all the DIs. We have this monotonicity in the indices. So we have here a E of maximum of x and E. Voila, and this is bounded by AE plus 1 of maximum. Because AE plus 1 is the iterate of AE. And we have here argument 2. So we have here at least well, this argument M is at least the biggest 2. We have at least 3 iterations. 3 iterations cover at least 2 iterations. So that's fine. So you see, you cannot fail. And finally, the last thing is dealing with this property. And this is more elaborate. So for sure, everybody here in the audience would have been able to come up to this point. Now comes a slight trick in dealing with the scheme of the primitive recursion. So assume finally if F is defined by primitive recursion from and H. Induction hypothesis gives what? We find 2 numbers E and D such that E of x is bounded by E of maximum and H of x. And now I have put in 2 more arguments because H has 2 more arguments and D. So I put them in over here. Defined by AD of maximum over x. Voila. That's fine. Now, now we have to make up an argument. Now the trick in the proof is we make claim. And to understand claim, you have to understand what primitive recursion is doing. Namely, we start with function g, and then we form iterates of h. H of h of h. How often? As often as this argument is here. Okay. So the claim is what? F is a function of limit x, and this is bounded by AE r plus 1 of maximum x. Well, I did maybe like for we have E and D. Let's see the maximum. E and D. And I put here C. And this is proved at induction The proof is easy. The trick in the whole proof is to come up with this claim. Once you have the claim, you are done. Well, you will see f of x and zero is by definition g of x. G of x is bounded by a index b, therefore by a index c. It's bounded by a index c. Now r is 0, equals to 1, that's fine. Maximum over x 0 and perfect. Easy, right? But you see, there's one trick in the proof, namely I have here r plus 1 and not r, because I need the 1 over here to make up the argument. Not a deep thing, but 25 minutes. Now this is step r equal to 0, and the second step f of x and r plus 1 grows like I have h of x, then you have here r, and then you have here f of x and r. Now what? This is bounded by, for h, I have this bound, was bounded by AB or maximum x and r, and this one. So this one is bounded by induction hypothesis by a c of a c r plus 1 times iterate right to the maximum and then you see this is bounded by B is bounded by C, is bounded by A C. Now one more iteration comes into play with R plus 2. Makes a maximum about this. Now make R bigger to R plus 1. And voila. This is the claim for R plus 1. Okay, claim is shown. Now, the conclusion is f of x and y is bounded by AC r plus 1 maximum x r and c. Now we see here he makes his argument one bigger. Then AC plus 1 is the iteration of AC. Well, we have here the iteration of AC. So here's the maximum taken over x. So we have found an index such that f of x r is bounded by a index c plus 1. That's the whole proof. And you see, it works by itself. And if you do the usual proof, you spend 1 double hour, and the 1 double hour is spent in figuring out how the classical Ackermann function interweaves with these functions. We make our life easy. We modify the definition slightly, and then we get the result. And to compare our result with the other one, then you have to do a small calculation how this Ackermann function relates to the classical Ackermann function. There's not a big deal. So this function, a of m, is basically bounded by the other Ackermann function, Ackermann of index m, and then take basically the argument 2 times m, or something like this. So that's not that a big deal. And I hope that this was informative. Maybe it was boring for some people, but maybe non-boring if you have never seen it. Fine. Don't worry, in a minute it becomes interesting. Because now we study Barrow Harrington. So next theory is what? It's a theorem which I don't prove. So it's finite Ramsey numbers. So did I define the Ramsey function? R V C of M is the least number R, so with the P from the D subsets of R and the C exists in the H and then in R, but that H is homogeneous and beneath of H exists the and what's known? The Ramsey function for pairs fulfills this part. C to the C of K minus 1. And B R to C of K is an exponential lower bound. 2 times C times K times epsilon of some bigger than 0. This is part of finite combinatorics. Oh, going to happen over here. We have to leave. Ah, yeah, okay, not a problem. So these are 2 bounds, which you find in textbooks on Ramsey theory. The first one is basically coming when you do the finite combinatorics proof of Ramsey's theorem. So you do the infinitary proof, you copy it, but you just work always with finite objects, and then in the proof you just keep track about the numbers showing up. And then you come up with this bound. So that's doable. This one you will have no chance when you try it by hand, because this has to do with ingenious proof by Erish, and he was using what is called probabilistic method. And you have never heard about it, you will not be able to come up with a proof. There's some tricky proof. So this proof is done by a sort of indirect argument that since a certain set has strict positive probability, something comes out. Can give some pointers to the literature, but it would take me too far, maybe 1 double hour just to cover this one. What I want to do is, I want to use those ones to get bounds on the following. So let's CF. Okay. Is the least number R subset of E. Subset of R and the C. Exit H and R homogeneous. And energy of H is as big as maximum of K and F of the minimum. And the question we are considering is, what is the growth rate of this function depending on function f? And now it's time for a break, so 15 minutes break. And after the break, I will do two things. I will give, first of all, good upper bounds when f is really slow growing. That's a very short proof using this bound. And then I go to approximate the Ackermann function when f is the form epsilon times binary log. And that's hard because, well, you see, when you have the Ackermann function itself, you directly see, if you define a function in this way, this function is quickly growing. It's very quickly growing. When you have here the function epsilon times binary log function, there's not the slightest indication that the numbers should start growing. Of course, you have an exponential lower bound, but it could stay forever in the exponential region. Say, we have exponential upper and lower bound. It could stay forever in the exponential region. But we will see, for some reason, it starts growing. But it's not the case. So normally, there's a natural occurrence of the Ackermann function. It's not that we put the Ackermann function in and get the Ackermann function out. The Ackermann function comes by nature. That makes it interesting. Okay, we will see it after the break. Now 15 minutes break, so it's 20. I start in 15 minutes. The question. Yeah.
But claim A, the exponents, so you have c to the power of c times k times 1?
Minus 1.
Ah, minus.
But times 1 would not.
Yeah, would not be right.
Yes, but in our purpose, the minus 1 is not important. It's some sort of exponential. So what's going to happen is 2 times the number times binary log of c. So the upper bound is a bit more than exponential in the number of colors. So here's just c, but not c. And it's unknown whether I can smuggle in here log c. But actually, if you are able to smuggle in log c, you will become famous.
Yeah.
So there's these Irish problems where you get $50 if you solve them. But of course, the fame you will earn is bigger than $50. Yeah. Okay. So I hope that you enjoy what's going to happen.
And are there also lecture notes of this? Or?
Not really. So I put on Ufora lots of papers, and this is one of the papers. I will give reference to this, but in some sense, I don't have lecture notes because the presentation I give is always different. I always choose different topics. Therefore, there's no standard lecture notes for this. At some moment, I could start writing up something. It's a global overview about everything. But it should, so the point is, it should be entertaining and of interest to the students. So when you give me a sign that certain topics are not so interesting to you, just let me know. There's possibility to switch. But I hope that this is fine.
Yeah. How is the evaluation of this course?
Als
we dan nog opnemen, dan moet je het Engels doen. Misschien wel alle mensen ook horen.
Normaal hebben ze
Okay, so what's going to happen is now those ones we have missed the first part. Well, we start basically at 0. So what do we have? We have 2 players here. One is standard Ramsey function, and the standard Ramsey function in general is like this. RDCM is calculating the least Ramsey number such that for all partitions of the D-Ramsey subsets of the Ramsey number, if you see many colors, they exist a homogeneous set having. Now here it's the H is homogeneous and it at least M many elements. Now, for the standard Ramsey function, when G is equal to 2, we have these two bounds. An exponential upper bound and exponential lower bound. I will not prove those, just assume them. And what I'm interested in is in the Peress-Harrington function, with respect to parameter function f. And this is the least Ramsey number R, such that for all partitions P from the two subsets of R into C, there exists a homogeneous set H for partition P, such that H has at least K many elements. And connectivity of the homogeneous set is at least as big as function of the minimum of H. And now we want to find out how does this function grow as a function of f. Now comes first some sort of new definition of the Ackermann function. But you believe me that this is the other one. Let's start now with the function growing a bit quicker. In the iteration, it grows a bit slower. But it follows basically the same pattern. And f of I. What I will use is this function f is non-primitive recursive. And we have just seen the other function I gave the proof. Now it's slightly less iterations involved, but you can cover this by making the arguments bigger. So if you replace x by x plus 2, then this function covers the other function. Okay, now I come to the definition of functional inverse for B. Unbounded.
Yes.
Yes.
Yeah, sorry. What is exactly the definition of R?
This is minus 0.1.
No, above. So that's R. Yeah, this one.
R2CF of K.
Okay. So.
Okay. So if you cannot read it, just let me know.
So f is a parameter.
F is a function parameter, yes. And the goal of today is to show when f is epsilon times binary log, that we get here an Ackermannian growth rate. And that's not obvious how it is possible, right? Because for standard Ramsey, we have just exponential upper and lower bounds, and out of nothing, we have to generate Ackermannian stuff.
So R2CF of K or?
Yeah, well, RT, the question is how to put this. So maybe it's this function symbol applied to K.
Okay, sorry, yeah. That's
Sort of
okay,
difficult to write it down. For B unbounded, non-decreasing, I define B inverse of A. You would expect it's at least K bigger than 0. I think B of K is at least. So if B is an exponential function, then B inverse is a log function, etc. Log will become, in this context, the binary log of I. And I define a function f m of I. It's log of I divided by taking fm inverse. Then round to the natural number. And if E of I is log of I divided by E of S of I, rounded up. Rounded down to a natural number. Now comes the next theorem. Namely, when is the growth rate of this function not so spectacular? And the general result is let B be the function and B be unbounded and non-decreasing. Let C be a number, and so on. Then we have the basic function R to C FB. Okay. And this is bounded by R to C of maximum taken over A B of C times log of C plus B C times log of C. So what is going to happen? Just assume that you take a function fm, not the full function f. Every function f index m is primitively recursive. So if you take f, then a primitive recursive function is the index function for fb. Fb is this function. If you have log divided by inverse of a primitive recursive function, then you get your message term, but the bound is in the primitive recursive function. And you get a primitive recursive upper bound. This describes one part of the phase transition, namely when I plug in here primitive recursive function for B, then the Pereselin function stays primitive recursive. Now the final upshot is if I replace here B by the Ackermann function, here I'm getting the upper bounds, but I will also get lower bounds. That is interesting. Now first, the upper bound. The upper bound is basically when we prove in one sentence, we apply this standard Ramsey bounds yield bounds for Pereselin in the situation where we have low complexity. Now, and actually in my presentation from last time, I've given the proof of Pereselin in the Peano axioms. And I was also just using a finite Ramsey number, and basically the same proof comes here, modulo some noise, but believe me that the proof is basically obvious. So I put down number T as maximum over K, E times log of C, and N is what? So I fix the number T. T shows up over here. Okay. N is the Ramsey number. Input T. Okay, and now let an arbitrary partition be of N plus B C log C. And you see the and this is what? It's basically the number over here. Now I have to show that there's a homogeneous set for this. Now what we do is we consider this partition on a shorter domain. So we have what? This number here, N plus C log C minus BC log C is N. And n is what? The random number. This applies that if we put P on the domain, left endpoint this number, right endpoint this number, then if we restrict the partition to that set, there's still enough element to apply Ramsey. So there exists an H contained in this interval, C log C, and here I have n plus b log C. Now one has to be careful with left and rightmost endpoint. Makes it count correctly. This interval has n many elements. So P restricted to the two subsets of this interval has, because we are dealing with the random number, has only the set H such that P is restricted to the two subsets of H constant. And the community of H, if you have the random number, community of H is at least the biggest. Okay, and now we have to show that the F largeness condition was also the same H. Then we obtain that community of H least as big as T, least as big as, and now we do a sort of trivial estimate. C times log of C times T. We do the same number here, P inverse F B C log C. This cancels out with this one. Now this is at least as big as what? Yeah, we have this interval. The left endpoint is this one. So if I do what? If I replace this number by the minimum of H, the minimum of H is at least as big as this number. I can here replace it by the inverse of the minimum. And here we'll have log of minimum. If this is the case, then I'm done, right? Because this is the function f index b of the minimum of H. I have to figure out why this number is at least as big as this number. Well, the minimum of H bounded by, now comes the trick from last time. Minimum of H is bounded by the maximum of H. Maximum of H is bounded by this number. So it's bounded by n plus b c times log of c. Bounded by. Now comes here for n. N is this Ramsey number. We get this upper bound for the Ramsey. Times 1 times log of c plus c log c. Okay, now we have to show that this number is bounded by to this number, because we have to show So minimum of h is bounded by 2 to the of this number, then log of this number is bounded by this. So this number here is bounded by the question is how to count the c. So here is c, let's see, times t divided by c. We can divide it by 2 plus log c. And this is bounded by, well, this is 1/2. I can show that this one is bounded by this one, and then this is bounded by 2c log c. And this number here is c log c is bounded by, now we have to look for t. T contains this number. So this is bounded by c to the c times -1 divided by 2. Because t is at least as big as this number. T is an exponential, c is bigger than 2. Exponential is bigger than the exponent. When in principle, when I would have done a miscalculation, it doesn't matter though so much. What you would do is you would make the numbers slightly bigger, then you can compensate for minor mistakes. But I think the calculation is correct. But what you see basically is the classical argument is here. Finite Ramsey yields Peirce-Harrington for simple functions. Yep.
Possible just to explain, I was just working with the steps and to explain just after the classic approximation I just underlined. So t has its property of being the maximum of h and the function b applied to whatever's written there. How do you get from there to the second, you call it second?
From here to here?
Yes, if you could.
Because P inverse of P is identity, and this cancels out with this, and then it's just T. T is at least.
Is it always identity? Since I thought inverse was defined as the least number, such that if it is applied to, then the number is at least as big as.
Morally, it should be the same, and otherwise, you just adjust somehow the terms.
Okay.
But let's just assume that B, the what?
But of course,
We can, in the applications, it will be a branch of the Ackermann function. So let's say assume that B is strictly increasing, then it's going to.
In any way, just you say it's a 3 set big, so it should, yeah, certainly be less than.
Yeah. So basically, the proof would be fine. Now, the proof itself is found in an article together with Menachem Kutschmann, Richard Lee, Omri, and myself. And it's an article from 2008. A bit older. But now what's the point? The point is the following, namely, that was the easy part. Now we have to do the Ackermannian lower bounds when B is the Ackermann function. And that's pure magic. So that was, so to say, easy.
The article is on 4 as well.
Yes, the article is on 4. And since it has been refereed, the estimates should be okay. And if they're not okay, don't worry. These arguments are allow for large applicability. So if you do a miscalculation, well, you have to know every now and then where you have to plug in your +1. Next proof lives on +1. So what comes the lemma? Well, it was theorem 8. Maybe it's not theorem 9. Theorem 9 is interesting. So we assume bound B over there. At least as big as 2 times k times 1 divided by C0. C0 is a constant, it's a positive epsilon. That's fine. Let D be a number. Epsilon is the 1 over D. F epsilon of I is epsilon times primary line, bound up downwards, and K is 2 times B times 2 plus 1. Then we have something, namely R2 C0 times B times 2 plus 2 F epsilon. Okay, is at least as 2 K times B for K and this is K. Now, that's the key result in the whole construction. Why is this a key result? First of all, we have this phase transition function epsilon times binary log. And I'm claiming that for this function, f epsilon will become Ackermannian. Now this is to be proved. Now we know we have an exponential and upper and lower bound for standard Ramsey. Now how to escape exponential bounds? Well, if you have a double exponential function, then you escape the exponential region. And that's the key, right? Once you left the exponential and you jump to a double exponential and you iterate further, you get the Ackermann function. Now, how is this achieved? Well, first, the epsilon is fixed. Let's see this one. And what we then do is, well, C0 comes by nature, but then we add here more and more colors. And if you have enough colors, so enough colors guarantee that I can kill the epsilon somehow. So epsilon is given, I make the number of colors big enough that I can compensate with the epsilon. And then I get double exponential. And once I have double exponential, you can imagine by putting in more colors over here, I get iterations of double exponential, and then I get the Ackermann function. I'm not fully done yet, because the upshot will be that this function will generate the Ackermann function, but then I finally replace f epsilon by f index Ackermann inverse, which makes it even more magical, because then the epsilon goes to 0 in function to arguments. This makes it even more complicated. But first, let's look how this is going to work. And that's a general strategy. When you do phase transitions, you first have to start with something, then you have to refine. And when you first you have to come up with constants, and at some moment you can make constants dynamic. And this is the place where the constant here is still a constant. Okay, and now you will see a beautiful proof, and you will not see what's going to happen. Just pure magic is one of the. I like this proof very much. And the reason, one of the reasons is that I did the proof by myself. So I'm very happy with this one. And well, when you see the proof, you will somehow judge with an idea of I like it. First of all, can you see the proof? I hope that you will like the proofs too, right? I hope. Uh,
K, is it just supposed to be 4 times Z plus 1? Because that's kind of,
That's capital K.
Yeah.
And small k is at least is capital K.
yeah, but why is it written like that?
4 times d is also fine. Just a bit of laziness of myself. There's no specific reason why I have 2 times 2. Maybe I should have written 2. Anyway, now comes the magic. So we have to, out of the blue, we have to generate the double exponential function. So, oops. And in some sense, what's going to happen is the following. The Ramsey function is an exponential function. Then you have the phase transition function, it's a log function. There are 2 players, one is making numbers bigger and the other is making numbers smaller, the log function. It's like with Bootstein, you have to set up a context where the function pushing something bigger is more powerful than the function trying to make something smaller. And the way how we can win this game is, first we fix epsilon times log, and then we figure out what power of exponential we need to kill epsilon times log. Okay. All wishful thing, right? So let small k be given. And 0 as a number, that's 0. Now what we do is we define number n1. N1 is R2 T0 k. And now, as I said, every now and then -1 is important. It's over here. This -1. And this -1 is important. And for I bigger than 0, if n plus 1 is not, it's ni plus r C0 times d times 4. No, I have to use 4. -1, 2 epsilon times binary log of ni. So let me stress, it's somewhat important to have here -1. Also important to have -1 already. What else do we see? Well, we do this for 1, strictly less than k -1. It's also important to have here another -1. How you can ask the question, why is it important we have -1 already? Well, finally, let n be n index k -1. So what do we learn here? First, we have to figure out how big is the number n. And as I said, number n is basically what I just said. We have 2 players. This function making numbers smaller. But the Ramsey function is an exponential function. So here you have you're setting up a dynamical system, right? The next function value is take the original one, make it smaller, and make it bigger. Now the number of colors have to be organized in a way, and finally something bigger comes out. So n will be double exponential. Okay, that's fine. My last question is, what has this to do with our original problem, right? Not the slightest idea. Well, the claim is there is partition P from this n 2/3 of n into colors C0 times D times 4. What do we see here? There's another -1 weighting. And the -1 is not showing up here. And there's partition P without subset, let's call it H, N, such that penalty of H is at least as big as maximum taken by K and yes, epsilon of minimum of H. What would this mean? This means that the Pereselland number is to be bigger than this n, because this is a situation I have a context n for which I can find a bad partition. Now, the Pereselland number says all partitions are nice. So this means this n has to be smaller than the Pereselland number we are hunting for. And I'm not saying yet how this P comes up, but if I have succeeded in proving the claim, the Pereselland number is bigger than this number n, and this number n is double exponential in K. That's the setup. Now the question is, where does the function P come from? And the function P comes from basically this -1, this -1, and this -1. You don't see it twice. Okay. First of all, well, we choose P0 from N0 and 1. So what is this? This is an interval, and this interval has a length shorter than the Remsenker. So I can find a partition, see many colors, such that all homogeneous sets can be smaller than K.
Yeah. C of C0. Then zero, C0 is subscript, subscript for n -1. N.
Question C also. Yeah. Well spotted. So we choose one such that for all H point in 0 and 1. Such that which are E0 homogeneous, we have infinity of H is smaller than 2. And this I find because I take the Ramsey number -1. So the Ramsey number is the first one where all partitions have large homogeneous subsets, but if I subtract the 1, there's a bad partition waiting for us. So that's the first one. It's coming in. Now we choose some more bad partitions, namely for those numbers. For this is smaller than K -1. Choose partition from Ni and I plus 1 square into 0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E0 times 4 minus 1, such that for all time homogeneous with H, we have E0 times E, E you have what? The penalty of H is smaller than this number. Okay, now we have a bunch of bad partitions. Now we have to do something with that. And it's still not clear what's going to happen. So basically what we have done now, we only have used what? That we have used this -1 over here and this -1. We have not used this -1 here. That is what we are doing right now. So what is the point here? We have what? We have here n0 and 1. And then we continue with n1 and 2. We have n2 and 3 up to n k minus 2. We have n k minus 1. We split the numbers below n into these intervals. Now define P from n0 to n, so from n into, and now we have one extra color. The extra color is one more than we have here. So one more than we have here. In some sense, we glue the partitions together. What we do is P UV is what? If U and V are in between N I, then PI is different. You can plug in here I of U and V. Now the trick, +1. So +1 serves I have here one extra element. Here's a -1, +1 is fine. And 0 otherwise. Aha. What is the claim? This partition P is this property. Do you see it already? Maybe not. So yeah. Make a discussion. So how is this possible? Well, two things. So P is good for the claim. So let H be homogeneous. So the claim is we have this P,
Okay.
and if H is P homogeneous, question?
Yeah, so I was wondering whether the partitions had to be onto functions on C, but you assured me so. Indeed, there's always an extra color if you increase my.
Yes. But what you see also in the argument is why slowly you need more and more colors. So if the number of colors would be bounded, the argument would break down. So to get finally the Ackermann function, I need an unbounded resource for colors. Anyway, so this function P is a bad partition. So there's no H homogeneous in this property. So take H P homogeneous, and then we have to show that H violates this condition. Well, case 1 is so P homogeneous means it has to have a fixed color. So it could be that the color is 0. if P and H2 is 0, what is going to happen? Well, could it be that two elements of H are in one of those intervals? The answer is no. Once you're in one of those intervals, you get a color which is different from zero. What does it mean? It means from every interval here, you have at most one element in the homogeneous set. Right? Now you check how many do you have? Just count the number and it's bounded by numbers bounded by k minus 1, which is actually smaller than k. So if this is going to happen, then the candidate of H bounded by the number of possible intervals, bounded by k. So H does not fulfill this inequality. Okay, that's fine. Now, what else can you do? Well, could be that the color is different, right? So it's sort of n+1. Yeah. Now one point which is important. Could it be that from H, one element is here and one element is here? The answer is no, because then the color would be 0. So if the color is different from 0, the element of H have to be concentrated in one of these subintervals. So if this is going to happen, then there is J such that H lives in one of those intervals from n to n plus 1. Now, on these intervals, I have colorings Pi. So if I'm the leftmost interval, I have coloring P0. So if there is a 0, then what? I have to check what's going to happen with some of these sets, and they have all candidates smaller than k. So if J is 0, then H is 0 homogeneous, follows candidacy of H is smaller than k. Therefore, this is not possible because here's k. Yes. Okay. And now comes the magic. Could be that J is bigger than what? Well, we look. What do we have here? Then we have homogeneous set for Pi. So it means candidacy of H is bounded by the number. So this so getting then candidacy of H strictly less than epsilon logarithm of nj. But H lives in the interval from nj to nj plus 1. The minimum of H is at least as big as nj. So bounded by epsilon not of that's a beautiful proof, right? Yes, you put down your partitions and by magic everything works out. And afterwards, you have not learned what's now finally the partition, right? It just comes by your existence. Anyway, what is now shown is, so this, the claim is n is smaller than R2 C times D times 4 of epsilon. Okay, that's good. So n is a lower bound for the Ramsey number, and then we have to show that this n is double exponential in K. But that's not yet shown. So it's a beautiful proof, but it could still be that we have shown the empty set. Because if this n would be an exponential function of K, nothing would have been gained. So what can we do? Next claim is Ni is at least as big as 2 to the 2 to the I times B times 2, or 1 is equal to I smaller than K. If this is true, then finally n index K minus 1 is 2 to the 2 to the K minus 1, but then K shows up in the double exponential. So we have to show it. Of course, it was by induction on I equal to 1. So n1 is at least as big, and here we use this one. The lower bound for the sun and this is at least as big as 2 to the K minus 1. Now, in the beginning, we have made some estimates. K is big enough, it's as big as capital K. Capital K is at least as big as 4 times D or whatever. It's bigger than 4 times 2 to the 4 times D. Just by making capital K big enough. So that's fine. Okay. If I is bigger than 1, we have epsilon times log of Ni. This one is at least as big as. Okay, the reduction hypothesis gives what? So epsilon times I times 2. Now epsilon is 1 over D, so it is so this means Ni by 1 is at least as big as finite rectangle. 0 times D times 4 minus 1 of epsilon times log of Ni. At least as big as what? Now we take again the finite Ramsey. Let's see, 0 times D times 4 minus 1 times number. And this is at least as big as the times 2. And yeah, so it goes. And that's basically it. And finally, what we obtain is obtain R2 0 times E times 4 of epsilon. Okay. This is because n k minus 1. This is because 2 to the k minus 1 times e times 2, which is equal to k minus b. So we jumped out of the world of exponential functions. And what you see here is basically this function f epsilon, and the number of colors is made big enough. So whether it's d times 4 or d times 5, it doesn't matter so much. But here's an exponential function. So d is 1 over d is epsilon. So d kills the epsilon. C0 is some starting value, and then you guarantee that this term here is much bigger than this epsilon. And then you have this fight of a strong exponential function, again a little bit weaker logarithm function, and when you iterate those, you get a double exponential function. So that's fine. And that's a proof. Now, at some moment, you could just believe the rest works by itself, and so this is the hard part. And of course, if this argument would not have gone beyond exponential, then all the rest would be empty. So okay. Plus 0 and 9. What comes next? Here and 10. Again, let epsilon be 1 over d. So d is equal to 4. Epsilon is 1 over d. F epsilon of 9 is epsilon times log of I. And then R2 C0 e times 4 plus m F epsilon. Okay, so at least as big as 2 to the d times m of k. Fm is this Ackermann function which I used in the beginning. So the point is, once you have enough colors, so many, you get the double exponential function. When you iterate your double exponential function, iterate, then you build up basically the branches of the Ackermann function. And so if finally this k goes into this index, then you have the diagonal function, and then you get here fk of k, and it's full Ackermann function. And that's the explanation why the Perestroika function starts growing. Okay, but so how can we prove this? We do induction on M. To prove by on M. The previous theorem covers the case m equal to 0. Okay, now assume then for m, let's prove it for m plus 1. Now we know how to do this. We set up a similar procedure. So what we do is what? N 0, 0. N1 is what? R. 0 times d times 4 times n. F epsilon. A minus 1. N I plus 1 is R 0 times d times 4 plus n. F epsilon of epsilon log of n I minus 1 for 1 I smaller than 1. And finally put again n equal to nk minus 1. Now you see again certain minus ones shown here. And they are used to produce partitions. And they are grouped together into a new partition. And the new partition needs one more color to use the construction as before. Okay, so plane. There is a P 0 n square into now 1 color extra. For all h, for P homogeneous H, we have community of H is at least as big as maximum taken over K and F epsilon of the minimum of H. Okay. Now the proof is basically the same, but with some minor adjustments. What are the adjustments? There's one trick, namely the Ramsey function is defined on sets of a given cardinality. So the cardinality matters. Peres-Harrington function does not only depend on the cardinality. So if you move your domain from small numbers to big numbers, the condition on the minimum changes. So if you have in the beginning a range where these minhomogeneous sets exist, and if you move your domain to a bigger domain, let's say if you move it to an interval far left out, there's no reason that you can guarantee the minhomogeneity. So it's not stable under isomorphic copies. So you have to take this into account. So it's not completely obvious how to set up the argument. Well, I'm not saying that it's complicated. The warning is only that the Peres-Harrington Ramsey stuff is depending on the order of the natural numbers. So the farther you go to the right on the interval, the more complex the condition on the minimum becomes. Anyway, we have these numbers. So let's P0 from N0 to N1. N2, 0, and 4 plus N. Such that comes by induction hypothesis. All 8 contained in N0 and N1. If P is homogeneous, H is P0 homogeneous.
So
Yeah.
I have a
Yeah.
question. The statement there will be that the cardinality of H is less than the maximum? Am I wrong?
This is not the case.
Okay.
Right. So I want to have a bad partition at this point. So every homogeneous set has to violate what you are right. It's my mistake. So P0 of H would be constant. And the tendency of H this one here, P of H is smaller than the maximum. Okay, and minimum. Okay. That's fine. That is how you would start, right? Now for what is the M. Choose one. And now we choose the same starting point. But now we I plus 1. Yeah, and 2. 0 times B times 4 plus N. Such that what H 0 to N plus 1. We have if PI if H is PI homogeneous, then we have that H is a small penalty. So what? Okay, this in the meantime this number, and otherwise we have mean homogeneity for F. This is smaller than the maximum taken over epsilon times log of mi. Here we have epsilon of okay. This comes just from the numbers. The Ni are defined so that we have existence of bad partitions Pi. And for this we use the -1s. Now we have to find out what is P. P defined on 0 and then N minus 1, which is N. And now we use the extra color. And the partition itself looks like as before. PUV is if you have Ni smaller than U, smaller than V, smaller than Ni. Then you have Pi UV plus 1, 0 otherwise. And we claim that this function P is having a property that for all P homogeneous sets H, we have its penalty of H is smaller than this one. Okay. Do we see this? No. So let H be then it could have color 0. If it's color 0, we do the argument as before. Yes, these intervals. If color is 1, then think of A and bounded by K minus N and K. Now assume that color is bigger than 0. Okay, we have these intervals nj and j plus 1. And we cannot leave these intervals. Once we have left one of the intervals, if one is outside, one is inside, the color would be 0. Then and some j and H j. Now two things. It could be that j is equal to 0. Then we look for P0 and we have this code. P0 we have this code. That's fine. Or then maximum and epsilon minimum. And this is what we are supposed to do. Now, the case J bigger than 3. That one is dangerous. Then it's going to have penalty of H bounded by this line. It's not that dangerous because H sits in the interval from nj to nj plus 1. If so the maximum is this number because nj is smaller than the min. N's bounded by the maximum of k of this number. Okay, so what's going to happen? The point is now that our Ramsey number.
Yeah. Sorry, the last inequality is it's bounded by the maximum of K and
K and
as
this
K.
one.
Okay, sorry.
So this is sort of
Yeah.
just to have this condition. This is sort of trivial estimate. Anyway, so what is the upshot? The upshot is that now this is beta partition P for this number of colors. So this means R2 of C0 times E times 4 plus M plus 1 of epsilon of K is bigger than N comma 1. So it suffices now to show that this number is as big as this number. That's not so clear yet. So claims what? Ni at least as big as 2 to the d times Fm I times iterated times number. Okay, how do we do so? By induction. And 0 was 0, right? Interesting. N1 is what? It was R C0 times B times 4 times M plus M. A minus 1. Now this proof of theorem 10 is by induction on M. So from M itself we have 3. And here is strict bigger. So if I subtract here 1, that is going to equal 2. So this is at least as big as D times this Fm. 1 times iterated to plus. It's basically by main induction hypothesis on M. Yeah. Now we apply the subsidiary induction hypothesis. So assume that this is true. We calculate what is epsilon times binary log of Ni. Epsilon is 1 over d. So epsilon cancels with d, and we get this number. The subsidiary hypothesis is epsilon log of Ni. At least as big as Fm by K, which in the case is as big as K, 4 times. And then we obtain what? And I have is what? R C0 times D times 4 times N. So let's have a look. Yeah, we have to take this into account. So I'll just write what is over there. We have the epsilon times log of minus 1. Yeah, the main induction hypothesis on M. If you have the 50 greater, so if I subtract the 1 over here, I have greater than or equal to. Greater than or equal to. 2 to the d times and m of this argument. This argument is already by substitute induction hypothesis m I times greater. Which is by method the d times fm plus 1 times. So you see how the world fits nicely together. Everything comes out by nature. And finally, you obtain what? N is nk minus 1. As big as 2 to the d times fm is k minus 1. And it's k. Which is by definition of this function 2 to the d times f m plus 1. Yeah, now you have seen a big result. So you just start with something and you do and do and do, and at the end you get full strength. Now the question is, I guess I have now to stop. Next lecture we will learn. So this is for the function f epsilon of I is epsilon times log of I. Then we go over to a new function where it's depending on I. And basically, when epsilon of I is 1 divided by Ackermann inverse of I, we still get Ackermann inverse. And that's even more magic because now epsilon is moving. And, how can such a moving element survive this procedure? More shocking is the proof will be much shorter than this one. There will be a sort of indirect proof which fits on one page where you can replace epsilon by epsilon of I. But I will explain it next time. Yeah.
You will probably rely on this proof.
Yes.
Otherwise, it would be. So,
Yes,
yeah.
we will rely on this proof. And what is the philosophy? The Ackermann inverse function of I behaves like the constant function when you plug in only primitive recursive functions. It works like a black hole. Whenever you plug in, it never starts growing. So it works like a bounded function. So this means you can replace this function by a constant during the calculation, and then you apply the result which we had today. And so therefore it's possible to come up with a very short proof. Moreover, what we will see is next time the Kanamori-Maclaurin theorem for regressive Ramsey functions. Kanamori-Maclaurin also comes with the Ackermannian growth rate. And then at some moment later, we will see the full Peres-Harrington result with dimension D. But before doing so, we need a bit more elaborate stuff on fast-growing functions. Okay, thank you for your attention. Yeah.
It's not, the paper on the Ufora also contains this proof.
Yes.
Okay, because
So
sometimes
everything is somewhere in some papers, and I will put the papers on Ufora, so to say. Except the last one with Botswana Weierstrass, it's not yet published, not even submitted. So it's a sort of work in progress, and depending on how far I can go, I will